Morning to everyone. This is Sunitha, Assistant Professor of Physics. Today's my topic is Introduction of Optical Fibers and a Numerical Aperture. Now see the first, what are the topics in the optical fibers? First one, construction and working of optical fiber. Second one, acceptance angle, acceptance cone, numerical aperture, and the relation between the numerical aperture and acceptance angle. Third one, types of optical fibers in terms of modes and in terms of refractive index profile. Next, fourth one, attenuation in optical fibers. Attenuation means losses. Next, fifth one, optical fiber in transmission and applications of optical fibers. Now see the advantages of fiber optic cables over copper wires. What are the advantages? Now see first one, fiber optic cables transmit data at much higher speed than copper wires. Okay, the optical fibers that transmits data is much higher speed than copper wires. Why? Because in optical fibers, the data is transmitted in the form of optical signals. So optical signals means light. So the velocity of light is the velocity of light is very speed compared to the electrons. Sorry, the speed of light is greater than the speed of electrons. So the optical fibers cables transmits the data at high speed. Second one, uh, fiber optic cables have a much larger bandwidth. Okay, they have the much larger bandwidth compared to the copper wires. In optical fiber cables, that is over 60 terabytes per second, whereas in copper wires, 10 gigabytes per second. Next, fiber optic cables have very low attenuations. Okay, these are having the less attenuations because repeaters need not to be added only after every 50 kilometers compared to the 5 kilometer in copper wires. Okay, in these optical fiber cables having the very less attenuation. Why? Because here we using repeaters at 50 kilometers every after every 50 kilometers. So what is repeater? Repeater is a device which generates the optical signals. So in optical fiber cables, we used after every 50 kilometers, but in copper wires, these repeaters are used in after every 5 kilometers. That's why in copper wires, the attenuation is very high. In optical fibers, the attenuation is very less. Next, optic fiber optic cables are not affected by the electromagnetic interferences and power fluctuations. That means uh, short circuits, there is no short circuits in the optical fibers, and they are minimally affected by the power failures. Fifth one, fiber optic cables are much more secured since they cannot be tapped easily. So these are high secured. Next, as fiber cables are made up of glass, they very less affected by the corrosive chemicals. Hence, they are much suited to harsh factory conditions in comparison to copper wires. So, these fibers are made up of the glass and these are less affected by the corrosive chemicals. Fiber cables are thin and lightweight. It's easy to carry these optical fibers because they are very thin and light in weight. Uh, the optical fiber cable weighs around 4 lbs per 1000 feet. lbs means libra, as compared to, whereas in copper cable, 39 lbs per 1000 feet weight. Next, the life cycle of fiber cable is 30 to 50 years. So lifespan is more compared to the copper wires. Fiber cables are superior to copper cables in terms of handling, installation, storage, less expensive maintenance, strength, and durability. Okay, these are easy to maintenance. Installation is also easy, and storage maintenance also very easy, and high strength and durability. These are the advantages of the optical fibers over a copper wires. Once we see, optical fibers are transmits the data at high speed, and they have large bandwidth, and they have very less attenuation, low attenuation, means very losses are very less, and they are not affected by the electromagnetic interferences. That means there is no short circuits. Next, these are very secured. These cables are made up of the glass, so these are less affected by the corrosive chemicals, and very thin and light in weight, and durability is high. That is 30 to 50 years. Lifespan is more, and these are easy to handling and installation, and they have high strength and durability. These are the main uh, advantages of the optical fibers compared to the copper wires. Now see, what is optical fiber? Okay, optical fiber is a cylindrical waveguide system which is made up of the transparent and dielectric medium which operates at optical frequencies. Actually, optical fiber is a cylindrical waveguide system which operates at optical frequencies. Means the light is passes into the core. Now see the construction of the optical fiber. Okay, now this is the diagram for construction diagram for the optical fiber. The optical fiber having main three parts, that is core, cladding, and coating. This is also called protective jacket. Core, cladding, protective jacket. So first, the central layer is called core. Okay, this is the central layer is called core, and the diameter of the core is 50 micrometer, and the refractive index of the core is N1. Okay, diameter of the core is 50 micrometer, and the refractive index is N1. The core surrounded by the second layer, that is called cladding. Okay, the core is surrounded by the second layer is called cladding. The refractive index of the cladding is N2, and the thickness of the cladding is 125 to 200 micrometers. And the cladding is surrounded by the third layer, that is called protective jacket. This protective jacket provides the mechanical support to the optical fiber and to avoid the damages from the moisture and abrasion. This is the construction of the optical fiber. So here, uh, the light launched inside the core at one end of the fiber propagates through the other end due to total internal reflection at the core cladding interface. Now see what is the principle of optical fiber or working of optical fiber. See here we have three cases. Here in these three cases, the light ray travel from the denser to rarer medium. Denser to rarer medium. Here we have three cases. Okay, in all three cases, the light ray travel from the denser to rarer medium, and the refractive index of the denser medium is N1, and refractive index of the rarer medium is N2, and always N1 is greater than N2. Now see the first case. When the light ray travel from the denser to rarer medium with angle of incidence I, where when I is less than theta c. Okay, the angle of incidence I is less than theta c. The ray refract into the second medium like this. Okay, move away from the normal and travel like this. Okay, when I less than theta c, the ray refract into the second medium. Now see second case, when the angle of incidence I is equal theta c. Okay, when I is equal theta c is a critical angle. Okay, when angle of incidence is theta c, the ray refract into the interface of the two media like this. Interface of the two media. When I is equal theta c, the ray refract and traverses along the interface of the two media. This is the second case. Now, third case, when I greater than theta c, the angle of incidence is greater than the critical angle, the ray reflect back into the same medium, that is back into the denser medium itself only. Okay, this is the total. This is called total internal reflection. Okay, when the incident angle is greater than the critical angle, the light ray reflect into the same medium is called total internal reflection. This is the principle of the optical fiber. When uh, here we find the theta c value, sin theta c value for this. When I is equal theta c, apply the Snell's law at second case. N1 sin theta c is equal to n sin 90. Okay, N1 is the refractive index of the rarer medium. N2 is the refractive index of the, N1 is the refractive index of the denser medium. N2 is the refractive index of the rarer medium. When we apply the Snell's law at this condition, N1 sin theta c is equal to N2 sin 90. Okay, angle of incidence, angle of refraction is here 90 degrees. So N1 sin theta c is equal to N2 sin 90. From this, sin theta c is equal to N2 by N1. Sin 90 is equal to 1. Okay, this is the principle of the optical fiber. When a ray of light travel from denser medium to rarer medium, and if the angle of incidence is greater than the critical angle, then the light ray gets totally reflect into the denser medium. This is the principle of the working principle of the optical fiber. Now see the derivation of acceptance angle and numerical aperture. Okay. For this purpose, first we see the cross-section view of the optical fiber. Okay, this diagram shows the cross-sectional view of the optical fiber, and this is the core medium, and this is the cladding, and this is the axis of fiber. Okay, axis of the fiber. Here the refractive index of the core is N1, refractive index of the cladding is N2, and this is the air. This medium is air, and the refractive index of the air medium is N0. Okay. Let the refractive indices of core and cladding be N1 and N2 respectively, and always N1 is greater than N2. Okay, N1 is greater than N2. Let the refractive index of the medium from which the light is launched be N0, that is the air medium. And let the light ray enter at angle I to the axis of the fiber and refracts at angle R. Okay, this is the angle of incidence. In the light ray enter into the core with angle of incidence I and refract into the core medium with angle of refraction R. The angle of refraction R. And this light ray incident at core cladding interface at point B. Okay. Now see first of all, what is acceptance angle? What is the acceptance angle? The maximum angle of incident at air core interface. Okay, this is the interface of the air and core medium. Okay, the maximum angle of incidence at air core interface for which the light ray and enter into the core and traverses along the core cladding interface. Okay, the light ray traverses along the core cladding interface. This maximum angle of incident is called acceptance angle. Okay, this angle of incident is called maximum angle. Sorry, acceptance angle. This maximum incident angle is called acceptance angle. When the light ray enter into the core with acceptance angle, then the light ray traverses along the core cladding interface. So now uh, find out the acceptance angle. Okay. For this, let us consider the triangle. See here the triangle ABC. Okay. A, B, C. Here the angle of refraction is R, and this is the angle of incidence. Again, here different medium. Core and cladding is different medium. This is the again instant ray out. Instant ray. The angle of here, the angle of instant is theta, and here the angle is 90 degrees. From this triangle ABC, the angle R is equal to, can be written as 90 minus theta. Okay, 90 minus theta. Okay, R is equal to 90 minus theta. Now, from Snell's law, at point A, now apply at point A, we apply the Snell's law, that is N naught sin I. N naught is the refractive index of the air, and sin I is the angle of incidence. Okay, N naught sin I is equal to N1 sin R. N1 is the refractive index of the core, and R is the angle of refraction. Okay, N naught sin I is equal to N1 sin R. This can be written as sin I by sin R is equal to N1 by N naught. Okay, sin I by sin R is equal to N1 by N naught. From this, sin I is equal to N1 by N naught into sin R. Okay, sin I is equal to N1 by N naught into sin R. Now, what is sin R? R is equal to 90 minus theta. Sin 90 minus theta is equal to cos theta. Now, substitute this value. Sin I is equal to N1 by N naught cos theta. Okay, we get equation 3. Okay, sin I is equal to N1 by N naught into cos theta. Here, let the limiting value for containing the beam inside the core by total internal reflection is theta c. Okay, let the limiting value for containing the beam inside the core by total internal reflection is theta c. Let I maximum be the maximum possible angle of incidence at fiber end face A, for which theta is equal to theta c. The, the meaning of this, when light ray enter into the core with acceptance angle, the light ray traverses along the core cladding interface. So when the light ray enter into the core less than the acceptance angle, okay, when the light ray enter into the core less than the acceptance angle, then here the angle of incident theta becomes, here the angle of incident theta is greater than critical angle. So when I is equal to I maximum, theta is equal to theta c. See here, when I is equal to I maximum means acceptance angle. Here the theta is equal to theta c. The light ray travels along the core cladding interface. When I is equal to less than the acceptance angle, then here theta is greater than the critical angle. So now we find out the acceptance angle. For this, I is equal to I maximum and theta is equal to theta c. So we find out the maximum acceptance angle. Maximum angle means acceptance angle. Okay. We find the equation for the acceptance angle. For this, I is equal to I maximum. When I is equal to I maximum, theta is equal to theta c. Now substitute these values in equation 3. We get sin Im is equal to n naught by n1 by n naught cos theta c. Sin Im is equal to n1 by n naught cos theta c. So we have sin theta c value. That is sin theta c is equal to n2 by n1. Okay. Sin theta c is equal to n2 by n1. From this, cos theta c can be written as under root of 1 minus sin square theta c. So now substitute sin theta c value here. That is equal to under root of 1 minus n2 square by n1 square. This can be written as under root of n1 square minus n2 square by n1. n1. Okay, this is the cos theta value. Now substitute this cos theta value in this equation. Then sin Im is equal to under root of n1 square minus n2 square by n naught. Okay, sin Im is equal to. So n1 cancel, remaining n naught is there. Okay, sin Im is equal to under root of n1 square minus n2 square by n naught. From this, the acceptance angle Im is equal to sin inverse of under root of n1 square minus n2 square by n naught. Okay, this is the acceptance angle. Okay, this angle I maximum is called the acceptance angle of the fiber. Now, definition of acceptance angle. Acceptance angle is defined as the maximum angle that a light ray can have relative to the axis of the fiber and propagate down the fiber, or the maximum angle at or below which the light can suffer total internal reflection is called acceptance angle. Now see the acceptance cone. So an optical fiber accepts only those rays which are incident within the cone having semi angle IM. Okay, what is the acceptance angle? Uh, Acceptance cone. An optical fiber accepts only those rays which are incident within a cone having semi angle IM. And the light ray contained within the cone having full angle 2 IM are accepted and transmitted along the fiber. Therefore, the cone is called acceptance cone. The cone is called acceptance cone. This is about the acceptance cone. Next, numerical aperture. The numerical aperture NA is defined as the sine of the acceptance angle. Okay. How we can define the numerical aperture? The numerical aperture is defined as the sine of the acceptance angle. So numerical aperture is determines the light gathering ability of the fiber. Okay. Numerical aperture determines the light gathering capacity of the fiber. It is a measure of amount of light that can be accepted by the fiber. Okay, what is numerical aperture? The gathering capacity of the optical fiber is called numerical aperture, and numerical aperture depends only on the refractive indices of the core and cladding. Okay, NA is depends only on the refractive indices of the core and cladding materials. A large numerical aperture implies that a fiber will accept large amount of light from the source. Okay, a large Na implies that a fiber will accept large amount of light from the source. So Na is equal to sine of acceptance angle. Sine Im is the acceptance angle. Then Na is equal to under root of n1 square minus n2 square by n naught. Okay. Na is equal to sine inverse of under root of n1 square minus n2 square by n naught. Finally, we get Na is equal to under root of n1 square minus n2 square by n naught. N1 is the refractive index of the core, N2 is the refractive index of the cladding, and N naught is the refractive index of the air, that is equal to 1. Okay. Now see the fractional index change. Okay, the fractional index change is represented by the symbol delta. Okay, the fractional refractive index change is the ratio of refractive index differences in core and cladding. Okay, it is the ratio of refractive index differences in core and cladding, that is N1 minus N2, to the refractive index of the core, that is N1. Okay, N1 minus N2 by N1. Okay, this is called fractional index change. Delta is equal to N1 minus N2 by N1. Okay, delta is a fractional index change. It is the ratio of refractive index differences in core and cladding to the refractive index of the core. Okay, now this is equation 1. Now the relation between the numerical aperture and fractional refractive index change. Okay, already we know that numerical aperture is Na is equal to under root of n1 square minus n2 square, and this can be written as n1 square minus n2 square can be written as n1 minus n2 into n1 plus n2. Yes, n1 minus n2 into n1 plus n2. Okay, now substitute from equation 1, that is fractional index change. Delta is equal to n1 minus n2 by n1 when delta n1 is equal to n1 minus n2. Yes, n1 delta. Okay, n1 delta is equal to n1 minus n2. Na is equal to, from this, Na is equal to n1 minus n2 is equal to what? N1 delta. Now substitute Na is equal to under root of n1 delta here and remaining n1 plus n2. Okay. numerical aperture can be written as, okay, under root of n1 minus n2 into n1 plus n2. So n1 minus n2 is equal to what? Delta n1. Okay, Na is equal to under root of delta n1 into n1 plus n2. If we assume n1 is approximately equal to n2, then this value becomes 2n1. Okay, if I assume n1 is approximately n2, then Na is equal to under root of, this is 2n1 and n1, 2n1 square and delta. Okay, Na is equal to under root of 2n1 square delta, and n numerical aperture is equal to n1 under root of 2 delta. Okay, this is the relation between the numerical aperture and fractional index change. Okay, Na is the numerical aperture, delta is the fractional index change. Okay, this is about the numerical aperture and relation between the numerical aperture and fractional index change. Now see the types of optical fibers. Optical fibers are classified into three major categories: the type of material used, the number of modes propagation, and the refractive index profile. Okay, based on uh, based on the type of material, these optical fibers are divided into two types: glass fiber and plastic fiber. Okay, based on the material, glass fiber and plastic fiber. And second one, number of modes of propagation. Okay, number of modes of propagation. Again, the optical fibers are divided into two types: single mode fiber and multi-mode fiber. Okay, single mode and multi-mode. And third classification, based on the refractive index profile. Okay, based on the refractive index profile, again that optical fibers are divided into two types: step index optical fiber and gradient index optical fiber. Okay, these are the types of optical fibers. So these types of optical fibers. See you in next class. Thank you.